We've got another example here for doing projectile motion in X and Y components. And this one, we are firing off of a higher surface and landing on a lower one. So we've got a change in our position in the Y sense, and we want to find our change in position in the X sense. They give us the total velocity. So we've got VA going up like that. They give us the direction on that, so that's nice. We've got our good old pal 345 triangle telling us how much velocity is in the X, how much is in the Y on the initial launch. So we could have 4/5 times 150 in the X, 3/5 times 150 in the Y. And we can use that for our different constant acceleration equations. And we also want to find t, the time in the air. So that'll be interesting. So we need to start thinking, what are our useful equations that we can use? We only have one in the x, and we have three possibilities in the y with any of these constant acceleration problems. So let's set up our x equation. That's the only useful one, right? This normally has the plus 1/2 at squared on the end. The a goes away, and we're just left with this useful piece of that equation, excuse me, which tells us the final position. So they're calling it XB, which would be position R, right? Equals the initial position plus the initial velocity in the X times time. So in that, we have a couple of unknowns. We are looking for R, that would be our final position. We know we're starting at 0 if we just call the y-axis 0 in the X. That makes sense. And then the initial X, we said, was with the 3-4-5 relationship, 4/5 times 150. So there we are with our initial X velocity. So we've got an unknown T and an unknown R. When we plug in the others, that's what we're left with. So we can't solve it with a single equation. We'll need to go to the y's to come up with something with those same two variables, or at least with the time variable, right? So let's come up with a y equation. I would probably avoid one that requires you to know the end velocity, right? Like the one that's like v final squared equals v initial squared plus 2a times s minus s naught. We don't want that one because we don't know the final velocity. So our third equation out of the set of three constant acceleration equations, that one's not going to work. The first one also has initial and final velocity in it. So that second equation that has the change in position, that's going to be useful because we know the change in the y position is 100. And depending what you want to call ground zero, if you like the lowest point being 0, then you could say we're going from positive 150 down to 0 for your initial and final. Or we could say we're going from 0 down to negative 150. And that's kind of how they've drawn up this coordinate system, is with the origin at A rather than at B. So in that case, we're going from 0 to negative 150, and that's our initial and final for A and B here. The initial y would be the 3/5 times 150. And the rest, we know gravity, we can plug that in. And the rest is the t's that we do not know. So we're plugging in all of those. Our initial, or our final position, initial was 0, so it's not there. 90 is the 150 times 3/5 times time minus 1/2 a t squared, where the t is still unknown. But now we've got one equation, we've got a quadratic equation, right? It's a second order polynomial that we can solve for t. And you can either do your classic quadratic formula, or I would definitely plug that into a math solver in your calculator. That'll make it, uh, a 1 minute solve or less instead of whatever the formula might take you. So solve that for t. There it is. Now I've got the time for the launch. That's a very long launch. And it's because when we plug that in, yeah, it's going 2,400 meters. So I guess that checks out. So there it is for that one.